Hi, in exercise W3 we'll be investigating the influence of inertia of the drivetrain on acceleration of the winch in an extraordinary condition when the fish net is stuck. The fish net is dragged behind the trawler here in this exercise, and the trawler will continue moving after the net is stuck because the big vessel cannot stop at once. What is special here is that the control system needs time to identify that the net is stuck, and in this exercise we have 1 second before the system gets to know that the net is stuck, and then the torque is removed from the electric machine, and it lets the machine to accelerate to give out the wire. We will be using the well-known torque equation. Here the motor torque is the holding torque our drivetrain produces, holding the drum, and the load torque is the torque produced by the pulling force through the wire, where the wire is wound on the winch drum and the wire is dragging the net behind. We will be solving the problem in a simplified way. So the torque equation will be linearized here, and instead of having the acceleration as a derivative of speed over time, we will have a difference of speeds divided by difference of times. So as a step 1, we need to find out how much the winch drum will accelerate. So we know that before the extraordinary situation happens, the drum is at a standstill. So when the net gets stuck, the vessel just continues moving forward at the same speed as before, because the vessel doesn't know what is happening, and the control system as well doesn't know what is happening. So it will take 1 second before the system realizes the problem and removes the torque from the motor. But anyway, during this first second, since the load torque is increasing very rapidly due to the wire extension, and the reference torque for the motor is kept the same, so due to this disbalance, the winch starts accelerating. And again, our task is to find out how much the winch accelerates during this first second. So after we found omega 2, we need to do a very similar calculation for the second step. So on this step there is no motor torque anymore, so control system removed it, just letting the drum to accelerate and give away the rope. So if the rope didn't collapse on the first step, didn't extend too much, then this second step is important to check. So maybe it is still okay, so it's still continuous extending, but not to the limit where it would collapse. And we need to do some extra steps maybe until we either see the rope collapses or we see that the system let the winch accelerate as much as needed, and the rope is not extending anymore, and then the vessel can just stop and bring its speed to 0. On the next few slides we are showing how to organize the calculations in Excel. So just stop the video to look into the cells and copy the same expressions as we are using. I think this will be helpful. Before now we assumed we knew the inertia, J. Now it's time to explain how to find it. So inertia of the system, inertia of the drivetrain, is made by the inertia of the drum, inertia of the gearbox, and inertia of the rotor of the motor coupled to the gearbox. But please note that the inertia of the motor J3 is multiplied by gear ratio squared, and since gear ratio can be quite high, for example 10, then 10 squared is 100, and then J3 becomes more important than J1 and J2. And in this exercise we just simplify and say inertia is just the product of I square and J3. So let's look into the DriveConstructor. So let's first find the motor inertia. So click on more and scroll to the right, and you will see moment of inertia in kilogram meter squared. And you see the two motors proposed have quite different inertia, almost double difference, and by choosing the different motor we can choose lower or higher inertia for the same gear ratio. But let's take a look at what happens if we change the gear ratio. So we increase gear ratio from 3 to 8, and we do the same, press on more, and we see moment of inertia is there. It is much lower than before, but we should remember we increased the gear ratio from 3 to 8, and since it is squared in this total inertia equation, so overall inertia can be even higher, even though the rotor inertia is lower. If we now add a stage, another stage to the gearbox, we, I believe, reduced inertia even further down. Yes, but again the gear ratio was increased, and if we square that number, so the overall inertia may increase as well. So of course we can play it with the motor type, because different motor types will have different inertia for different configurations. And that's it. Thank you for watching.